Missed it. Okay. Yes. So please remind me of the questions that were left unanswered. Yeah. First, let's do the unanswered questions from last time. Okay. So unanswered. Sorry, it's too thin. Unanswered from last time. They will hopefully be simple because we have discussed them more or less. Yeah. So please remind me. Yeah, so that was there. Before that, there was a first question, right? There was some polynomial 0. Right. So as a function, if this is 0, that's right, fx. Now if, so let's write it here. That's because that's the question we want to first do. If fx is equal to 0 for any x, which means it is 0 as a function. When you are viewing it as a function, then it is 0. Then show that a3 equals to a2 equals to a1 equals to a0 equals to 0. Yes. Yes. So please tell me what you guys have tried. Just start. Don't wait for the other person. So we said that a0 is 0. That we had done. So maybe I'll just write here proof. See, this question is significant, right? Because it would then mean that being 0 as a function is same thing as being 0 as a polynomial, right? Polynomial was defined as some, as an algebraic entity whose 0 meant that each coefficient is 0. Okay, but as a function also, because it can take in inputs, when it is 0, we want to show that it is the same as polynomial being 0 as a polynomial. So yes. So why is a1 0? Let's just prove that, or I don't know. I think last time I think I had suggested that you should try to show a3 is 0 or something. Yeah, maybe. So this comes from f0 equal to 0. F0 means at x you put 0, so then you got this is 0, but this is just maybe the right way to write it is like this. A0 is equal to f0 is equal to 0. So that is fine. But why are the other things 0? That is what we want to understand. Okay. Right. So we can forget about a0 actually, that is not there anymore. Okay, then. Yes, but why? So from here, okay, what I can say directly from here is this implies that this thing, this is like a new function. If you want to name it, it's not necessary. This function, then gx is 0 for all x not equal to 0. That is the problem. For x equal to 0, we cannot say that this is 0 because x could be, because x is 0, right? So that makes it 0. So the second factor doesn't have to be 0. So then we cannot use the same thing to say that a1 is 0. Because we cannot put 0 anymore and use that. Because that is f of x divided, gx is basically f of x divided by x. You could say that, yes. It is not the exact same thing, but yes, it is, yeah. No, say louder. No, you can take it as anything, but how do you use it to say that gx that a3 is 0 or a2 is 0 or a1 is 0? If I've understood you correctly. You can, yes, you can say that gx is 0 for x not equal to 0, but how do you use it? That is the question, right? Well, no, that is the thing, because when you put g of 0, you cannot say, cannot we cannot say that g of 0 is 0. That is the difference, right? This thing, see this piece, this one need not be 0, because this is x. When you put x equal to 0, this becomes 0, due to which this whole thing becomes 0, right? So the other factor doesn't have to be 0 a priori. In the end, it will be, but so far we cannot say it from what we have got, right? Yeah. Okay. So here is a since we see, I had said hinted at this last time also. I think uh, there would be other methods, but I think try to show that a3 is 0. It makes sense to do this also. Try to show a3 is 0, because then you see, then it will sort of be an induction, right? Then you don't have to worry. Once you show a3 is 0, the problem is done, because a2 being 0 can be shown in the exact same way, I suppose. And there is a very simple reason why a3 must be 0. So again, the hint, see why I'm saying a3 must be 0 is because the idea is, okay, let's say that a3 is positive. Okay? So let's say that a3 is positive. And what does this imply? What does this imply when the value of x is very, very large? Yes, right? That is what, now that obviously we have to make that rigorous. We have to try to make it rigorous, but this is the idea, right? Look, you see, if a3 is 0, then if x is, now this is what we have to quantify. X is very, very large. I should just say very, very large compared to the other three terms. Yeah. Then f of x has become positive. And I mean, this is, I suppose this is just, means intuitively it's clear, right? I mean, it would be impossible for anything else to happen, right? Because it's x cube, right? So when x becomes very, very large compared to a2, a1, and a0, right? Then it will dominate the value of the other three, right? Even if these three are negative, even if these three are negative, it will still dominate it. And that is the point, right? So let's say that a2 is less than 0, a1 is less than 0. Let's assume the worst case in which all these three are less than 0. Okay. And you're putting a very, very large value of x. Then what happens? So a3x cube, what do you want to say? You want to say that this thing. So, I mean, we want to say this. I mean, first of all, is it intuitively clear? Because you have to first know that you have to prove it. Then only you would try to prove it. Is this? I mean, is it? Yeah, it should be believable, very, very believable. Yeah. Then if you don't prove it, also it's okay to some extent, but we'll try to prove it. So give me an estimate of what this x should be so that you can surely say that this is positive. Give me an estimate of x. Estimate x. These are some small bits which will be useful for us even later. Oh, no, but you don't know about A2, A1, and A0, whether they are 10-digit numbers or minus, negative of 10-digit numbers. So it has to be comparative with A2, A1, and A0, right? It has to be comparative with those things. Yeah. So we can try to do something like this. So let's try. Yeah. But do you see, right? Does everybody see? It has to be comparative with the other three. They cannot be a global value of x. That's the point, right? Given a2, a1, and a0, like this, if this a2 is minus 10 to the 10, then you have to take your x accordingly. And if it is just minus 1, then you have to take your x. Then, then it's easier to find the x, maybe. I mean, just saying. Maybe what you can do, just saying, is you can first do this. Can we say something neat and clean? What should I put in place of x so that I can surely say this is positive? Again, it will depend. It will be dependent on these three things. So, I mean, how about just take it 3 times to be the maximum of these three things, right? So let's just erase these things, and yeah, this is fine, right? We want to make it positive. What is the value of x that we should consider? So let's say that. So let's 1 minute. So let's take mod of, okay, so mod of this, I mean the positive part of this, okay? I'm just saying because it's a negative number, right? So you take the positive part of it. And then similarly, you take the positive of this. And you take these small estimate things we have to learn how to. Because see, we all know that there is some x, but what is it? Can you say something of it about it in terms of these three? That is an important thing to just have. So you just take this, just the positive parts, yeah, because these are all three are negative numbers, um, and then what you do is you take the max of this, right? That makes sense. Take the max of this. I mean, let's just call it t. Yeah. Then what should I take as x? Is it okay to take it to be t? Let's try, right? Let's try. So if you take it to be t, then this becomes t cubed, right? See, unless we try, we won't know how much we have to adjust, right? Can you say this is positive? Okay. Do you think it is positive? No, so there it may not be positive. It's not correct, right? So can anybody say, let's think. I shouldn't try to rush it because even I thought it is positive earlier. So now I'm seeing it's wrong. Let's see. Exactly. Yeah. I mean, in fact, all three could be t, right? So yeah, simply just if this is t, you see, it doesn't work. If a2 by a3 is t, then it becomes t cube. I mean, t meaning minus t. Yeah, if it is minus t, yeah, you see, it just fails. This is 0. If a2 by a3 is minus t and it can be that, then it is 0. And the other, this is already negative. So it's not positive. So we have to adjust. So what should we adjust it to? So please let me just say this again. If a2 by a3 is minus t, we are just learning these estimates. Okay, these are the, you don't have to do this all the time. The way this, what the goal mathematics does is the small estimates, we make theorems out of these and then we use them. So you don't have to do estimates in every problem, but right now we don't have many theorems with us. So we are, yeah. This a2 by a3 could be minus t is what we are saying. And in that case, you can see that it becomes minus t cube. And this part is already negative. So it does not work. So what should we do? If you take 3 times t, 4 times, it still does not work, I think. Or does it work? Let's see. It might work. So should we take, so what should we do? How should we adjust it? So I'm just erasing this. So you can refer to the x on the expression on the top. You want to make this positive. Certainly it has to override those 3 negative numbers, but just taking it to be the maximum of them doesn't work. So what should we take? Come on. No, if you take lesser than t, okay. I mean, so if you take lesser than t, like t minus 1, t minus, should we take t minus 1? I think it will not work, right? I think it just gets worse, right? If you take t minus 1, you see, I think if again the a2 by a3 is minus t, yeah, this is surely negative. So we want to go in the other direction. Just correct me if I'm wrong. Okay. Just leaving it there. Just correct me if I'm wrong. Okay. Reciprocal of t. Let's try. So if we take 1 by t, let me just put it and then we'll think. Yeah. I don't think this will always work. No, this will not work. But please think and say why this will not work. I think I am sure this will not work. Yes, yeah, you can say it like that, or you could also say that yeah, that is good enough. Or I was thinking, what was I thinking is that if you, yes, so in a lot of cases it will be smaller. Yes. Also what I was just thinking is, this is t cube, no, it becomes like this also, t cube t square. It's just the same problem, right, that we had with t earlier. almost the same problem, I think. Yeah. So, I mean, in that case, you could take, something, and it will not work. Like you could take this to be 1, you could take this to be minus t. Yeah. Similar kind of problem, I think. Yeah. It may work for some values, but that's not the point, right? We want to make it work for all values. Okay. Let's try 3t. Okay. Let's try to take 3t and see. Then this becomes 9t cube. Then this is a2 by a3, 4t square, 3t. Do you think this will be good enough? So I should write, I should write 3t. Just scaled it up by 3. Oh, yes. So that's why Ishana asked me. Yeah. That is 9t square. Yes. Yeah. Right. Sorry. So will this work? This will work, right? No, it cannot be minus 3t, right? That's the point. The max is t, right? So the max is t. So what can you say? So a2 by a3 is less than minus t, less than equal to minus t. It's not more than it's not, no, sorry. It's greater than equal to minus t. Sorry, huh? It's greater than equal to minus t. Is that right? I mean, that's what it means to say that its magnitude is not more than t. Its magnitude is not more than t. So the number cannot be lesser than minus t. I could draw it and show, but just think, right? Think it. 2t might also work. Yes, 2t might work. Let's put 2t. Doesn't matter. Yeah. 2t I didn't put for a certain reason, but I think 2t will also work. Yeah, 2t will also work. Yeah, I was just trying to be safe and put 3t. Yeah. So then you can just work with this only. So you see then 4 times this is bigger than 1 minute. So what is this? 1 second. So a2 by a3 is bigger than minus t, bigger than equal to minus t, right? So then can we multiply both sides by 4? Yeah, is that right? Yes, that's right, right? Nobody's saying because why? Yes. So a1 by a3 is, again, you see, it will just work, right? a1 by a3 again bigger than minus t. Okay, so I am just making a mess. It's t square, I think. So this becomes t cube. You just simple things, just work it out. A1 by a3 is again bigger than minus t. So again, 2 times t of this is 2t square, and no. So let's just let's write it. It's getting a little messy. So a2 by a3 is bigger than minus t, and so 4t cube, 4t square is bigger than this 4t square. Okay. Then this a1 by a3 is again bigger than minus minus t. So you have 2t times this, and that makes it 2t square, right? So there is seems to be a small problem. And this is again bigger than minus t, right? And so we have this. And then we add the 8t cube. So finally, what do we get? We get this thing, right? So let's check if that is positive. So then we have 8t cube minus 4t cube minus 2t square minus t. Is this always positive? No, right? This is not positive when t is small, when t is less than 1. No, when t is small, it doesn't work. I mean, right? Is that right? Yeah. So this is positive if t is bigger than 1. Certainly, right? In fact, that is what we had in our mind when taking, that's what at least I had in my mind when taking 3t cube, when taking 3t as the x. All right. So yeah, so I mean, certainly this thing, but this thing works when t is bigger than 1. Okay. But then you see what is left. I mean, the what is left is when t is less than 1, right? But then that case is even easier, right? I mean, if these things are, minus 0.2, minus 0.9, and things like that, then certainly you can take x to be some 100 or something and it will work. Certainly, right? You can. So that case is again easy. Is that fine? Yeah. So you see, you looking forward, we don't know the solution straight away. But looking backwards, we know, right? When you try and then you see, okay, for t greater than 1, it is true. And so for t less than 1, what should I do? But then for t less than 1, then this is simple, right? Then it just means it's like that, minus 0.2, whatever. And for that, you can just take x to be 100 and just say it. Or can you do better? I don't know. Take x to be 1 maybe. 1 will not, but 2 will work maybe. Yeah, 2 will work. That's easy. Yeah, that you can do. So that is the point. Is it okay? I mean, then all of them have to be less than 1, right? Because the maximum is less than 1. It's all of them, the magnitude has to be less than 1. So they have to be like minus 0 point something. That's easy. So is it fine? Just tell me if it's okay or not. Okay. So it's not such a, it was not a very silly question, right? One has to do these estimates to see. Obviously, once you do it, then you don't have to do it again. You know that. Yeah. But since we have done so much work in this, we would like to prove one very interesting thing. We would like to put this work to maybe some other place here. So let's see, there is an interesting question that comes. Okay. So far we have shown that this definition is the same, but the interesting question is like, okay, what happens if for all values that say is not 0, can we say it is 0 for at least one value? Can we say fx is 0 for at least, you see, that's the other end, right? At least one value. So you would know that it is not true for quadratics, right? If you have done any quadratics, you would know that it looks like this and it is not true. And I mean, you don't have to do all this. You just know, you just take x square plus x plus 2, right? Or whatever, 2, whatever. Then it's easier, but it's either way true. Yeah. I mean, so we are looking at real solutions. If you know what complex means, that's okay. But when we ask this, I mean all real numbers, numbers we know, or the numbers on the number line. So for quadratics, it is not true. But let's ask this for cubics is what I'm asking. No, yes, no, that's the exact question. Will there be a root Yes, that's all I'm asking. That's what I'm asking. Will there be a root? Like for quadratics, there need not be a root. At least a root that you, I mean, a number, a real number for which it is 0. There need not be, right? An ordinary number. But for cubics, is it true that there has to be such a number, or again, what? Yeah. Well, we do know that there is x. I mean, let's say x. Let's just say like this: there is a m such that f of m is greater than 0. Okay, by the way, let me just assume, and it's okay to assume, right, that a3 is positive. Okay, also, I am assuming that a3 is not 0. Why am I assuming that a3 is not 0? Because if a3 is 0, then it is not an honest cubic. Then it becomes a quadratic. So the question is different, but I am trying to ask for an honest cubic. So because we've done this analysis with x cubes and so on, so we want to use it. So a3 is not 0 is the assumption, or whenever someone says it's a cubic, then a3 is not 0. So let's assume, and we can assume it's positive, because if it's negative, you can multiply it by -1, make it positive. It will not change the fact whether it has 0, blah, 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 but it's, yeah. We know that there is a m, some m, we just discussed that, for which it is positive. That much we know. Can we say that it is 0 for at least some x, or same thing, just the word root you can use, but it's the same thing. Doesn't make the problem easier. This is a very interesting question. Okay. Okay. Let's see what others say. So now, if you can try to think of an example. Give us an example for which, and then someone can try to prove you wrong, or we can see, or then it will be. Yeah, what did you mean by ±1? That thing. Yeah, but if you put -1, then what do you get? You get -12 plus 5. Yeah, so this is -12 plus 5 is how much? -7. That's just, yeah, -7. So you found a value for which it is negative. See, you have not found the 0, but you have found a value for which it is negative. And you know a value, yes. Yes. So does everybody see that? This is a fundamental idea. So we need to start drawing. We are definitely lacking in drawing. That's right. So we should start drawing the pictures. I mean, just draw things. Just see, there is a value 1 for which it is positive. Whatever the value is, 17, right? It is 17. 17 is here, right? And then you find a value. So what am I plotting? I'm just plotting on the x coordinate, I'm plotting the input. On the y coordinate, I'm plotting the output. Just the usual way we plot graphs, but just saying, okay? On the x coordinate, I'm plotting the inputs and outputs on the y coordinate. When you put -1, you get something negative, right? You get -7. That's the interesting thing. So how can it happen that it doesn't cross the x-axis? it would be very strange if it doesn't, doesn't cut the x-axis at least once. It has to. There's no way it doesn't cut the x-axis. Somewhere it has to cut. Where it will cut, we don't know, but we know it will cut. Is everybody agreeing to that? Right? So see, we have not proved it and we will not try to prove this. This is a hard theorem to prove. As easy as it may look, when you try to prove it that there is some value for which it is 0, you will fail. See, the reason is that, see, what was the nature of the previous problem? We actually found the x for which it was positive. We found some 3t, right? In a sense that we didn't find it, but given the other things, we know that we knew an estimate. Here, it's impossible to say. What that x is, it's impossible to say. Even with the 5, 2, and 7, 3 given to you, okay, for cubic, there are formulas, but for higher degrees, there is no formula. But anyways, but it is that x cannot be described. Just think, okay? And these are the theorems in maths which are interesting, right? Because these are, it's like, you don't know that x, but you know that there is an x for which it is 0. Okay, this is maybe the first theorem. We can say this is the intermediate value theorem. Okay? Now you can try to ask yourself why that name, and tell me next time why is it called the intermediate value theorem. What is the theorem? The theorem is that if for so for any function that is a good function, okay, but let's just say polynomials, okay, for any polynomials, if p of alpha is greater than 0 and p of beta is less than 0, then p of c is equal to 0 or some c which is between, let's say alpha is less than beta, doesn't matter, you can, for some c, and that c has to be between alpha and beta, you can surely say. Yeah. And this is very easy to believe. So that's all we will do for now. We will not try to prove it. Because see, when you try to prove it, the question that really it comes down to is what is the real numbers? What's the definition of real numbers? And those questions are not easy to answer now, and not we won't lose anything by not answering them now. So this is called the intermediate, and you can just see look this up on the internet also. It's a very interesting theorem. Yeah, but then I don't know. Yeah, so this will be very interesting. So yes, there is some value, at least for that cubic, there is some value for which it is 0. Please tell me if there is any doubts. Because these small pieces, if you're comfortable with, then multiple of this you can do on your own. But if you're not comfortable, then you will not be doing it. Because okay, this is a 1 hour or 2 hour a week. Other than that, you have 100 hours maybe. Okay, I mean whatever. So yeah. So, please tell me if something is not clear. Or so see, it will not necessarily be rational, right? Because all you can say is that if you look at this picture, right, all you can say is that there is some x, there is some place where it cuts the x-axis, right? And where it cuts the x-axis, what does it mean? It means that the input value is something where it cuts and the output value is 0. So you know it's a root. So some place it cuts, but what that place is, whether it's rational or irrational, or we don't know actually. Okay, we don't know. Yes, that's another interesting question. So that's a question we will come to. And also, when can we say that it cuts at a rational, and when can we say that it cuts at an irrational? That's also a very interesting question. At least these 3 questions we can try to answer. Right? Those 3 questions will lead to good things. Okay? But first, let's make it very clear for everyone for the general case of the general cubic. So we have learned from the small example basically that answer seems to be yes, but I would like someone to say it clearly so that we are sure. And that's a major theorem, right? I mean, that any cubic has a root. Think about it, right? You proved something which is a very mathematical thing, right? In the sense that there is no straight answer to that, but it's true. It's nice, nice thing. Now let's just think about the general case of the cubic before moving to the other two questions that have come up. Yeah, just I'll come in 30 seconds. Just think. Yes. So you just want an explanation, more or less it's clear, but we want an explanation as to why any 3-degree polynomial will be 0 for some x. Yeah, someone has. No, so that first of all, that cannot happen. But the reason why, so why do you think that can happen? So we are assuming A3 is positive, right? Yeah. So if A3 is positive, then it will have a positive output. That's we proved that earlier, right? That when x is very, very large, then it becomes positive, right? We proved that, right? Now, I mean, just symmetrically, when x is very, very small, it must become negative, right? And see that has to happen, right? There's no way that you have to prove, but it will be true. Does everybody agree with that? Right? I mean, just the same way, right? I mean, if we put x equal to very, very small, it has to become negative. There is no other way, right? Because when you put minus x cube, minus cube of minus x is, minus of x cube, whatever, right? So it becomes negative. So by the same, this is the fantastic thing about odd powers. So it's not just about cube, but it's about odd powers, right? There is a symmetry. Right? So so similarly, when you put there is a m for which is negative, yeah, very, very small. Just like we found a very, very large, you can just basically tweak that thing, we minus t cube or something, whatever you can do, very, very small you can get, right? Very, very small x, very, very small x, or very, very small m. I'll just not use all these things now, and just say that there exists a m. There exists an m for which it becomes negative. Just by this whatever we use to prove this, this will also happen because of the odd power, right? That thing that was becoming dominating, which was a positive dominating thing, now it's a negative dominating thing, so it will make it negative. The thing is that it dominates, right? So when it becomes negative, it makes everything negative. Simple, right? And then whatever we just talked about, right? So it's positive at something, negative at something, so it will be 0 at something. Okay, so the answer is yes. I mean, just this result itself is a very interesting result. Okay, we have proved it from the perspective of looking at it. So just notice this thing, right? Polynomials, we are looking at it as a function, and the root is a functional thing, you could say, right? And we have used this, looking at it as a function, we have proved these things. Okay, but the root is also an algebraic thing. What is it algebraically? Algebraically, it is a factor, right? At least one value. If this value is alpha, then it is just a factor of f. Being a little vague here because we will not pursue this now. But you see, right? This we proved last time, right? There is some alpha for which the polynomial becomes 0. It means that, I mean, that is the functional language, right? But by the remainder factor theorem, it means that x minus alpha is a factor of fx, right? If alpha is value, because the remainder and so on is 0, and you can. So that's what it means algebraically. So algebraically also it can be proved, but let's not go into all that now. Yeah. So let's just erase this and write the theorem, because this theorem you're going to use continuously. I mean, you can use it many times. You could use it continuously also when you do continuity. Yeah. But what we have proved is any odd degree polynomial has a root. This maybe we can put it in a box and treasure. This is a good theorem. Yeah. But we have seen that even degree polynomials need not have a root, because we just know, right? But conceptually, why does this not work? Why does it, why does the same reasoning not work for quadratics or 4 degree? Yeah. So what reasoning? Reasoning where some value it is positive and some value it is negative. Why does this reasoning not work for even degree polynomial, or for, let's say, quadratics? Yeah. Well, the reason is that when you, let's say, you put very, very large value of x and it becomes positive, but then when you put very, very small, it will again be positive, right? Because, x square, so it will make it positive again, even if it's very, very small. So what does it mean? It means that there is no guarantee. Obviously, it can still have roots, but that reasoning doesn't guarantee that it won't have a root, that it will have a root, that it will have a root. It doesn't guarantee that. It may still have, obviously, I mean, the minimum is, down, then it still, if it's below the x-axis, it may still have a root, but you don't know. So I'm not writing it. Yeah, that's just an explanation. Very simple. So basically, this, you can appreciate this and use more of this graphs, and you never know how much you can get out of these graphs. It may look like, but a lot of things you can see first before trying to prove. Okay. But ultimately, these things are just a model to try to prove things which are already true, which we want to be, true, whatever. So yeah, drawing the pictures is a good thing. Right. So let's just do one last thing. So today I'll just stop on time, also because of my own interests. But yeah, even though I started late, but I'll make it up. As I've said, I'll make it up. Let's do the last thing that we had. So the question that we had last time is that any quadratic. So let's write that. Okay, any 3 input. Sorry, this one got extended discussion, but we got something out of it, so it's good. As long as we're advancing our knowledge, it's a good thing, and it's in a direction that these things are there, useful things. So any um, any three input output values. Did we show? Yes. Oh, the very first question, yes, because if A3 is not 0, then the value can be positive, right? That we showed, right? So let's see. So if there is, so going back to, is the first question, right? Or the only question we did actually. Yeah, this thing. So what did we show? We said that, okay, if, so we kind of did it by contradiction, right? So if A3 is positive, let's say it's positive, that implies that f of something, there was some large m for which it is positive. What does it mean? It means A3 cannot be positive. Similarly, it cannot be negative. Okay, so it implies A3 is 0. Once you prove A3 is 0, then it's induction. You see, in this way, you can even go for n degree and you can do the same argument. Okay, and then this one you can do by the same reasoning, or you can assume that, first, I mean, a naught is 0, you have proved. You can assume till to the power n minus 1, you can assume you have proved, assume it's true, and prove for the nth power. That's nice, right? That's the thing. And so that's nice thing. But yeah, one doesn't need to say induction, because really the n is fixed or whatever. Yeah, it doesn't matter. It's not fixed, but anyways. Yeah. Now the next thing is any three input output values determine a unique, yeah, that was the important thing, quadratic. It's a quad, and when we say quadratic, we want to say an honest quadratic. Honest quadratic, okay. So how do we do this? Yeah. Let's write things, yeah. So let's say that fx, so let's say f is the quadratic, and let's say, so again, I'll just write variables, okay? Please tell me if this is not comfortable. I will try to, I'll change it, simply change it to numbers, okay? But initially I'll just write like this. So let's say it's beta 1 something, and alpha 2, beta 2, and alpha 3 is. So, I mean, how can we say from here that, so there are two aspects to this, right? Let's try to show that there cannot be more than one quadratic. Let's first try to show that. Yeah. So first try to show that there cannot be more than one quadratic. And how do you think about such a thing? Well, because there are three variables and you get three equations, and so you should get a unique solution. Yeah, that's a rough reasoning. That can also be made precise, but that needs some other kind of language. But we try to prove it. Because there are easier ways to prove it. So how do we say that there cannot be more than one function, more than one quadratic? That is the first thing. So let's finish. I think what we were doing last time is we took equal values. Is that right? We took equal values and tried, right? One meaning? Okay, yes, yeah, okay. Yeah. Anyway, so that's fine. So now we want to say that there cannot be more than one quadratic. Yeah. So now let's see. So let's convert this information into a root information. What do I mean? I mean, see, you take something like fx minus beta 1, right? Now this becomes 0 for alpha 1. Is that right? Yeah. See, this thing also you can consider, isn't it? This is also a polynomial, right? This is also a quadratic. Yeah. I mean, let's just keep it to be 1 only. This one is 0 for alpha 1, alpha 2, and alpha 3. That's basically what's written. So now we use that algebraic thing about the zeros. So it is 0 for alpha 1, it is 0 for alpha 2, it's 0 for alpha 3. What does it mean? Well, it means that alpha 1 is a root. That's what it means, right? So it means that it's a factor. That's what we showed algebraically. So now we are going algebraic. If you go analytically from here, that at 3 values it is equal to 1, and you want to say that for all values it is equal to 1. That's what you want to say, right? Analytically from the graph, that seems difficult to show, because a graph doesn't completely capture the polynomial fact. Yeah, but the algebra captures that more precisely, the polynomial nature. So that is a subtle thing, right? For the graph, or for analysis, or for that kind of thing, that kind of a analysis, it is more like just a function that rises and falls, and it takes every value in between. It knows those things. It doesn't really understand that the cubic. That's the kind of thing it is. Okay. For it, a cubic and 5 degree is same. For analysis kind of graph kind of thing. I mean, it's not the same, but it is similar. Not much difference for it. But the algebra is more precise in this case. That's what I'm trying to say. So the alpha 1 and alpha 2 are the roots. And you will get something here, right? I mean, this will be something you will get remainder factor, right, when you do it. But then you also want a alpha 3. So how can you have an alpha 3 which also kills it, right? So first, is this fine? This thing from the two roots that you have. So you see, you converted this to a root information. This value information, we converted it to a root information, because 0 is a special number. 0 is the only number that when multiplied with other things gives you 0. If there is no 0, the number system will be not very interesting. Okay, at least the multiplication will not be interesting. There is a sort of a singularity, right? It's 0. 0 is the interesting thing. So that's how we convert it to 0, and then we can actually understand the factorization. So this is fine, because alpha 1, alpha 2 are 0, so they are factors. So you get 2 factors. Obviously, you cannot get 3 factors because it will become a cubic. So now there's a clear problem, right? Now, how can you have an alpha 3? You cannot accommodate an alpha 3, right? Because if this is 0, then what does it mean? So obviously these three are distinct. Otherwise, it doesn't make any sense to write alpha 3 here. This is a problem, right? This means that A is equal to 0. But A cannot be 0. I mean, A can certainly not be 0, right? If A is 0, then the whole thing is 0. It's finished. Yeah? I mean, A should not be 0, but then A is 0. So that, what does that mean? I mean, it means that this is 0. So what does that mean? It means that fx is not a quadratic, it's just 1. I mean, if you want to say that. I mean, it means fx is always 1 for any value. So just first see if this is clear. We are using the factor. Yes, that's a good question. Strictly speaking, no. If I say quadratic, then there is no quadratic. So what I've written on the top, unique quadratic, that's in fact not correct. I should say at most one quadratic. That's right. Or if you want to say the degree can be at most 2, then it's fine. But if you want to say quadratic, then it's not fine. That's right. Yeah. So yeah, in a way, there is no quadratic, but there is at most one polynomial, and that is constant. Is it fine? Yes. See the way. Yes, but initially, but that is but as I said, that is it. They are distinct. We should assume that, right? Because that's what we mean when we say 3 values are given, 3 inputs, right? So they are distinct. You have to assume that from the beginning. Yeah. Let's say we assume that it makes sense. Yeah, that these 3 are all distinct. You can, yeah, they are distinct. These are distinct numbers. That's, we are assuming that. Yeah. Otherwise, the question changes. Yeah. Yeah. So The thing to appreciate here is how we are using that every factor kind of reduces the degree by 1. Every root gives a factor, right? So what we have proved is the following, that any n degree polynomial cannot have more than n roots. I mean, that is a fundamental theorem, right? That is a very important theorem. That's what we have essentially shown, if you think about it, right? You can think about it for a cubic. Any n degree polynomial cannot have more than n roots. Oh, this is a very nice regularity thing, right? I'm not saying it has n roots. I'm saying it doesn't have more than n roots. Let's just reason it for a cubic. See, if you have a cubic and let's say f is a cubic, okay? So n equal to 3. And let's say that there are 4 roots. Then when I say 4, then I mean that these alpha i's are distinct. See, this is some very nice thing, right? If for 4 values it is 0, well, I can just use the factorization, right? For first value it is 0. So what do you get? You get a factor for it, and then you get this qx. But then at alpha 2, again f vanishes, but the first factor cannot vanish, so the other factor has to vanish, so you just factorize that. But then you keep factorizing it, and then what do you get? Get this, and then you get this. Now when the turn of alpha 4 comes, then you notice the problem. You cannot have a 4th root, right? Otherwise the whole thing becomes 0, right? When you put alpha 4, then this again, because we are saying it as a distinct, this is impossible. So here we are using the fact that product of 2 non-zero numbers is non-zero. Why I'm just said that is because that is almost all that we are using. Okay, so you can see if it's useful later. Okay, so we had now n minus 1. Why not n? It can have n roots also. Why? What's wrong with n minus? Why it can have n roots? Huh? Yeah. In fact, maybe at some point you can show that it will never have n minus. Well, no, it can have. There are some. No, 1 minute. No, so at some point you can show that it can never have n minus 1 roots. It can have n minus 2, but not n minus 1. You can show that at some point, hopefully. Those are more interesting, more and precise statements, but you'll see that later. So this is fine, I guess, and it's okay, right? Now this cannot happen, and so otherwise a is 0, then it's not, then everything is 0. The a is just that leading coefficient that you keep getting. That's a fundamental thing we have proved, right? Now using this, now that you have this, you can try to build this to, and this, let's not do it now, otherwise we'll be back to the same extended time, which we don't want the habit of. Rather that we start early and now try this. So first focus on the uniqueness. Assume that there are 2 of them, then you see their difference will be 0 at 3 values, which is sort of a contradiction you will try to prove. And whether there is one at least that you can try to try to prove. Yeah, in the sense that, okay, so let me change the question. Let me just also say, just to make sure that there is one. Otherwise, I just saw, right, that may not be. So this is in some sense wrong. I should just say less than equal to quadratic, meaning linear or 0 or constant. So, but anyways, now to make it precise, I'm just making all these 3 numbers also, outputs also distinct. Now that there are 3 distinct outputs, you will get a quadratic, but you have to prove it. And second thing is there is not no, you won't get two quadratics. You can only get one. And we'll try to use what we have done today. Okay. So yeah, that's all that there is. This remainder factor theorem is a very popular theorem, and you will find plenty of questions on this. I will set some just till Wednesday a little bit. Yeah. After that, I will do. But just see, I mean, just Google remainder factor theorem, brilliant. This, yeah, you will find in many places. But I will do it. I'll also do some interesting. Okay. So that's it for today then.